Let's talk about Ampere's law. Okay, before we get into this, let me remind you, this Ampere's law is similar to the Gauss's law, which I don't know if you remember, but what Gauss's law did was, okay, so here's a Gaussian surface. Okay, this is what Gauss did was, okay, he related the electric field on the surface. So this is an imaginary surface, this Gaussian surface, and you can do this for any surface. So this is the Gaussian surface. We will even give it a name. And so what Mr. Gauss did was gave us this relationship. He said the surface integral was equal to the charge inside divided by epsilon naught. Okay, so if you do the surface integral over this surface, and you can do it over any surface. So for instance, you can do it over this surface, and well, of course, the electric field changes, but the charge inside is the same. And so for these two surfaces, this surface integral would be the same. All right, so very similar to this is Ampere's law, which is what we're going to talk about now. Okay, so this was charges, and now we're going to talk about currents. So here's a current, okay. I1, I2, I3. So let's say we have a current flowing like this. And what you can do is, what Mr. Ampere says is, so these guys produce magnetic fields all around. What Ampere says is, if there's a magnetic field like this, and this is ds, okay. So B dot ds, okay. So you take the line integral around that loop, it could be any loop, is equal to mu naught times I inside. I inside is what is the current, total current threading this loop. Okay, so what is the total current threading this loop? And that's Ampere's law. So this line integral along that curve, and this can be any curve, okay, is equal to mu naught times the I inside the current. So there are three currents inside this loop, and if you go along in this direction, when you take the line integral counterclockwise, then these currents are positive and this is negative. If you take the line integral along this direction, this current will be positive and these will be negative. Okay. So again, the sense is with your right hand. If you use your right hand, and hold your thumbs straight up like that, and if you're going around the magnetic field in this sense, then those currents are positive. Okay. All right, so if you go around like this, then these currents are positive. Okay. That's Ampere's law. Okay. So for instance, if you do this line integral along this curve, the outer curve, okay, and you go in this sense, this current is going into the sheet and these currents are coming out of the sheet. Those will be positive currents and those will be, that's a negative current. So the net current is 6 minus 2, 4 amps. So it would be mu naught times 4 amps. The value of this line integral along this curve would be mu naught times 4 amps. Do next equations, you can do this line integral only in very symmetric cases, right? So we'll show you an example where you can do the integral, and we're just giving you the results. Okay, so this is Ampere's law, which is the parallel of Gauss's law. Gauss's law relates the electric fields on the surface of a two-dimensional surface, giving you the surface integral is equal to charge inside the surface divided by epsilon naught. Ampere's law relates the line integral of a magnetic field around a one-dimensional loop, and that's equal to mu naught times the current threading that loop. All right, so imagine this thick wire, and there's a current flowing through this wire, and the dots indicate that the current is coming out of the page of the paper. Okay, so this is a cross section, and you can use Ampere's law, that line integral, to show that the magnetic field at the center is 0, and you see the magnetic field, well, the magnetic field lines are circular, and as you move away from the center, the field gets stronger and stronger. The red arrows are magnetic fields. Okay, so what this diagram is showing you is the magnetic field strength gets stronger. It's strongest at the surface of the wire, and then once you're outside the wire, the strength starts decreasing again. Okay, and that's what's shown on this graph. The magnitude of the magnetic field is 0 at the center. So it's showing you, this graph is showing you the magnitude of these vectors, the red vectors. Okay, and so the magnitude of the red vectors is greatest at the surface. And then once you come out of the surface, you see the magnitude is decreasing, and that's what's shown. Okay, so here's the mathematical expression for R greater than R, the radius of the wire, the magnetic field strength falls off as 1 over R. And for R less than R, it increases linearly. Okay. All right, again, this result is gotten by doing this line integral. Okay. All right, so now we'll talk about a toroid. So here's a toroid. Essentially, go take a donut and wrap a wire around it, and you have a toroidal solenoid. Okay. And the point of this is, what this does is, if you pass a current through it, what it does is it produces magnetic field lines like that. And what is the use of magnetic field lines? We saw in the last chapter, a magnetic field line will trap a charged particle. Okay, so remember, if you have a magnetic field line like this, you take a positive charged particle and oops. So okay, so this positive charge, oops, we'll get, let's see, how do I draw it? Positive charge particle will spiral. I'm getting. Will spiral along the field lines like this. Okay. So what this magnetic field line has done is trap this charged particle. And so if you can have a plasma that's millions of degrees, at millions of degrees, this hot gas gets trapped around. And the idea is the charged particle traps around and it never hits this wire. And that's what we saw last time, if you were in class last time. We saw the tokamak, which was the fusion reactor. Okay. So here is the tokamak, that's the toroid, and inside this region produces strong magnetic field. So the magnetic field lines are like that. and it'll trap a plasma. See, the plasma never touches the walls. Okay, and that's the idea. Okay, so let's see. Yeah. So there will be the plasma, and the plasma never touches the walls of the chamber. Okay. So that's a toroid, and you can produce a strong magnetic field, and it can be shown that the field outside the toroid is zero. Okay, so there's only a field inside, and the magnetic field, the magnitude of the magnetic field is given by mu. N, capital N, is the number of turns in this wire of the wire. I is the current, and R is the radius of the toroid. Okay, and so N 2 pi r is the circumference of the toroid, and divided by that gives you little n, which is the number of turns per unit length. Okay. So the magnetic field inside the toroid is given by mu naught, the number of turns per unit length, times I. Okay. So if you want a strong magnetic field, you can either increase I or you can increase N. Okay. So in these plasma reactors, the hotter the gas, the hotter the gas, the stronger the magnetic field you need, okay, to trap it. So to make sure that it doesn't hit the walls. Okay. So anyways, so that's one of the reasons why we use these toroidal shaped solenoids. Here's a plain old straight solenoid. Let's show you a straight solenoid. Okay, so here is a straight solenoid like that. And again, essentially, if this is a very long solenoid, it creates a magnetic field inside, and outside the magnetic field is almost zero. See, in this diagram, you can see that the field is very strong inside and almost zero outside. So if it were an infinitely long solenoid, the field inside is uniform and outside is zero. Okay, so, and this is a cross-sectional view of this. The blue lines are the magnetic field lines. So these currents are coming out of the paper. This is a current going into the paper. And again, the field is mu naught Ni. N is the number of turns of wire per unit length. I is the current through the solenoid. Okay. And here is solenoid. All right, so now you might ask, why would we need this, something like this? Okay, so here's at CERN. So there's the solenoid. So there's wires wrapped around it, and look at the scale of this thing. That's a person there. All right, so at CERN, so here's a 60-kilometer ring, and the solenoid sits there. Okay, and proton, antiproton, or beams will collide. They'll collide here, and they make the beams collide here. And so when they collide, well, they annihilate each other, and all kinds of junk comes out, and stuff will come out. Yes, so what in this solenoid, you have a magnetic field in this direction. Okay. And this thing is filled with detectors. It's packed with detectors. Okay. And as particles travel through these detectors, they leave a track. All right, again. So here is the solenoid. This thing is packed with detectors. Okay. And there's a strong magnetic field in. And at the center of this detector, the beams collide. And when they annihilate each other, from that energy, all kinds of particles come out. And so that solenoid is filled with this magnetic field. And what that magnetic field does is, so here's a cross-sectional view. So the collision happened there, and particles are produced, and these tracks are laid in the detectors that packs that solenoid. Okay. And from the curvature of the detector and the direction in which it moves, you can tell if it's a positive or a negative charge, and you can tell the mass of the charge. Okay. So the mass of the particle. So from this data, you can figure out the mass and charge of the particle. Okay. So, we use solenoids for that kind of stuff. Okay. Anyway, at UF, there's a group that makes detectors that goes into this solenoid. So this is the kind of stuff when you have proton beam collide. This is the kind of stuff. A lot more junk comes out when two gold nuclei collide. So from the radius, you can tell the mass of the particle. Yeah. All right, I'm going to pause again and